everyone, my name is Nama Ben David, and today I want to tell you about the NVTraverse framework, which offers a general way to persist data structures on NVRAM. Now, the title of our paper is that the destination is more important than the journey in NVRAM data structures, and I hope that during this talk you'll understand why. What I want to do is actually start with a quick crash course on NVRAM, and for that purpose I have a diagram of a computer with its memory hierarchy. So here we have the CPU, the cache, the main memory, and the disk. Now, when there's a system crash, the CPU stops executing, we lose the contents of cache and main memory, but whatever is on disk remains there. And NVRAM is this new technology that can replace DRAM as the main memory of the system, but actually gives us the persistence that we normally get on disk. So whatever is there when we have a crash will remain there when we recover. And unfortunately, this is nothing changes for the caches and the registers, so those remain volatile and will lose their contents. Ideally, we'd like to use NVRAM to design faster, persistent algorithms. However, there are a few challenges, and in particular, we have to be prepared for the system to crash at any time. So let's look at an example for it. Let's say that we have an operation that wants to update these 3 memory locations. It's possible that we get through 2 of those 3 updates, and then we experience a system crash. Now, at this point, there's a question of when we recover, we might not have the data on the registers for the process to continue from where it was. So there's a question of, is this memory state consistent, and can we recover from it? Now, even worse than this is that, remember, we don't actually write directly on the NVRAM. We go through cache, and cache is not persistent. So let's say that we have our updates, and we actually write all 3 of them on cache. Before they're persistent, they actually have to be evicted from cache and written onto memory. And cache evictions can happen out of order. So in particular, it could happen that the second update reaches memory before the first. And if we have a crash at this point, we're actually in an even worse inconsistent state, because this state not only is in the middle of an operation, but actually would not have been reachable in a normal execution without a crash. Now, luckily, there's a class of algorithms called lock-free algorithms that naturally deal with the first of our 2 problems. And the idea of lock-free algorithms is that we don't allow a slow process to block the progress of any other process. So again, let's look at an example to make it more concrete. Let's say we have a process P1 that's executing an update on this data structure, and in this update, it wants to modify these 4 memory locations. And let's say that it gets through 2 of its 4 modifications, and now it pauses for whatever reason. At this point, if another process P2 comes in and wants to execute an operation, lock freedom guarantees that P2 will be able to do so, regardless of whether P1 continues in its execution or not. So really what we get is that every state, even ones in the middle of an operation, is a consistent state, which is great. So if we remember our NVRAM challenges, we were worried about inconsistent states that happen in the middle of operations, and with lock freedom, we actually don't need to worry about this. So lock freedom just naturally takes care of this problem. However, we still have our problem of out-of-order evictions, and this is still a big problem for lock freedom as well. Most lock-free algorithms are designed assuming sequential consistency, and if that doesn't hold, then they break. So the tool that we have to fight this out-of-order evictions is actually using explicit flush instructions. So the idea with explicit flush instructions, again, let's say that we have our 3 modifications on cache. We can execute a flush on a cache line, and that pushes that cache line from cache to memory, which is great. This is what we want. However, the flush instruction by itself doesn't guarantee that the flush will complete by the time that we continue our execution. And so in order to guarantee that we complete, we have to execute a fence instruction. And the fence will block our operation until the flushes have completed. Okay, and so this is great. And so we can use flush and fence instructions to fight this out-of-order eviction problem. However, these instructions are very heavy because they suffer the latency of actually accessing memory instead of cache. So we want to limit their use. Now, I just want to mention that for the rest of this talk, I'll be using just the word flush, and I'll always mean that I want to flush and wait for it to actually reach memory. So you can think of it as I want to execute a flush and immediately a fence. So now I think we have enough background to have a statement of our results, which is that we give the NVTraverse framework that gives an efficient general construction to take a large class of lock-free algorithms and make them persistent on NVRAM. Now, what I want to do for the rest of the talk is actually give you a little bit more background and talk about related work. And then I'll discuss the NVTraverse scheme and show you its details. And finally, I'll talk about experimental results. So the first thing I want to do is think a little bit, how can we use flushes to take care of our out-of-order problem? And the first thing that might come to mind is actually to flush out after every update, right? And this makes sense, right? If we were worried about updates being out of order, let's flush between each update. This should take care of our problem. Now, unfortunately, this is actually not enough. And the problem stems from inter-process dependencies that go through cache and actually miss the flushes. So again, let's make this more concrete with an example. Let's say that we have two processes and they're maintaining a shared memory linked list. So here we have the head of the list, and each of them wants to execute an insert operation. Okay, so let's say that P1 starts its operation, reads the head of the list, swings the pointer to its new node, and then is about to flush, but then pauses. And meanwhile, P2 comes in, reads the head of the list, and this time it will read P1's new node because it can read through cache. It will then swing P1's next pointer to its own new node and flush this node to memory. Now, if we crash at this point, what happens is that not only do we lose P1's insert, but we also lose P2's node because we don't have a pointer from the main list to it in the memory. And so the problem that we experienced here is that actually P2's update depended on a read that it did in cache that wasn't persistent. Right, so this sort of shows us that flushing every update is not enough. So what the literature has is sort of two broad classes of approaches for this. One is a very general approach that will work for all lock-free algorithms. And what it says is don't only flush the updates, but actually flush every time you access a shared memory location, flush it out to memory. And this is true for reads and updates. Now this is great because it's very easy to use, very easy to apply to any algorithm that you have, and is correct for any lock-free algorithm. However, it's very slow, right? In effect, it's saying, forget about the cache, always suffer the latency of memory. Now there's another approach called the hand-tune approach, which is to say, for every algorithm that you have to persist, carefully reason about the dependencies that you have between the reads and the updates, and see where the dependencies don't exist, you don't have to flush. And this can actually be a very efficient approach. So in this way, you can actually eliminate quite a few flushes. However, it's a lot of work, and every time you have a new algorithm, you have to start over and reason about that one. So let's go back to the statement of our results. I told you that we have an efficient general construction for a large class of lock-free data structures. And here, by efficient, I mean that we don't flush everything. And by general construction, I mean that we do apply to more than just one algorithm, we apply to a broad class of algorithms. And so now you have the background, let me give you a few details about what this broad class of algorithms is and how we do it. So the key insight behind NVTraverse is that many operations in common data structures actually start with a large traversal phase, after which the update that we execute actually doesn't depend on it. So again, let's look at an example. Here I have a tree, and I want to insert the value 6 into it. So what I would do is actually, I would start by traversing the tree on this long path. And once I find the leaf at which I want to insert, then I'll make a few small modifications to insert my new node. And the interesting thing to note here is that once I found my destination, I don't really care what values I read during the traversal. And in particular, if this 7 was an 8 instead, I really don't care, right? It doesn't affect the modifications that I would do when inserting the new value. And so the insight for NVTraverse is that for such traversals, we don't actually have to flush. And we only flush the parts that come after the traversal. And this is actually where we get the name of the paper from. So we think of the traversal as the journey of the operation, and the place where we do the modification as the destination. And we say that the destination is more important than the journey because that's the only part that needs to be flushed. Okay, so I gave you this sort of very vague intuition, but making this concrete is actually non-trivial. So it's not clear how to define what part of an operation counts as a traversal and what part counts as the destination, right? And this is actually the bulk of the technical meat of the paper goes into defining this. And so we define a class of algorithms called traversal data structures that have to satisfy certain properties. And we use these properties to sort of separate between the traversal phase and the phase in which we make our updates, and argue that there are no dependencies between them. Now, once we have a data structure that is in traversal form, we show how to automatically insert flush and fence instructions into it to make it into a persistent version, which we call the NVTraverse data structure. And for the NVTraverse data structure, we guarantee that it's correct for persistence, so it won't lose updates that have already completed. And this is the main contribution of our paper. Now, I do want to add that many lock-free data structures in the literature actually don't quite fit the traversal form as is, and they're very close to it, but do require some modifications before our framework can be applied to them. So what I want to do now is to just give you a hint of the intuition for what these traversal properties are. So remember, the intuition we're going with is that we want to flush all the reads that we depend on for the updates, but we don't want to flush the reads that we don't depend on. And so really our goal is to very clearly delineate dependencies from non-dependencies. So in a traversal data structure operation, we actually give it some structure in which there's first a traversal phase and then what we call a critical phase where the update happens. And we make these phases each be a function, and this helps us control the information flow. And so in particular, we give the input of the operation into the traversal phase and feed its output into the critical phase, which then gives the output for the operation. And this is really nice because now we can very clearly and formally argue about what the critical phase could depend on from the traversal. It's only the parts that were output, which is great. However, we still have to think about how the output was calculated. So let's focus in on just this traversal phase. Right, so the first property that we require is that the traversal is read-only. This is sort of a trivial property from what I've told you so far. And the second property, which might be a little less intuitive, is that we require some locality when making decisions in the traversal. So in particular, let's take our tree example again. And when we execute the traversal on it, it needs to take this format of reading one node at a time. So in particular, for every node, you read it, you're allowed to use any data on this node to make the decision of which pointer to follow next. You decide on that pointer, and from now on, you're actually not allowed to use the data of the node that you just read. So in essence, you forget the data from that node. And finally, the return value for the traversal is the last node that you reached, the place you decided to stop in your traversal, plus the pointer into it. So these are, at a high level, the properties for the traversal, and there's more details in the paper. But the nice thing to notice is that actually these two first properties are naturally satisfied by most data structures in the literature and all lock-free data structure algorithms that we looked at. So in particular, the traversal is almost always read-only. And usually, if you think of any traversal that you know, the decisions of which pointer to follow next are made locally based on the node's value. So most data structures already satisfy this. And the one thing that isn't just already satisfied by algorithms in the literature is that the traversal phase isn't nicely separated from the critical phase. And usually they're just put in the same function and we want them separated out into separate functions. But this is usually a very easy modification to do. Right, so I told you about our traversal properties. In the paper, we actually also specify some properties that the critical phase has to satisfy, but I don't have time for that now. What I do want to say, though, is once you do have a traversal data structure, we have a very simple way of making it into an NVTraverse data structure that guarantees correctness under failures. And this framework actually says to flush in two simple places. First of all, flush the output of the traversal. And secondly, during the critical phase, flush everything. So flush after every access to shared memory. And just as a practical note, this actually eliminates a lot of flushes. So in our experiments, we never flushed more than 6 locations per data structure operation. And this is even for very large data structures. Great, so those were our results. And I'd like to use the last minute of my time to quickly show you just a taste of our experiments. So we actually ran our experiments on 2 different machines, one with Intel's newest NVRAM technology. We implemented 5 different data structures and we compared to 3 competitors. I only have time to show you one result, so I'll show you a result on the linked list. And what we do here is we're looking at a linked list implementation with 16 threads with 80% reads and 20% updates. What we're seeing is throughput, so higher is better. And across the x-axis, we have the growing list size. And so a few things to note right away is that the NVTraverse version consistently outperforms the other general constructions. So the red one is the flush everything construction that I talked about, and the green one is a transactional memory framework. And under all settings, NVTraverse outperforms them. And I'm sure you noticed that, at least in this setting, NVTraverse is greatly outperformed by the hand-tuned version. And this is to be expected because when you hand-tune for a specific algorithm, you can find more lack of dependencies to capitalize on than when you're doing something general. However, what I want you to also notice is that as the list grows, we actually grow more and more competitive with the hand-tune. And for a large list, we actually outperform the hand-tuned version. And this is intuitively because when the list is larger, the traversal part in which we don't flush is comparatively larger as well in the overall operation. So that's all I have time for. I just want to leave you with this summary of our contributions, and I hope you enjoyed the talk.